All right, let's dive right into this explainer. Today, we're using Dr. Nima Matidian's highly structured technical framework to learn exactly how to translate physical machine logic into programmable logic controller code. Look, if you work in industrial automation, you already know that bridging the gap between a physical machine and the software running it, well, it can sometimes feel like translating a completely foreign language, right? And the stakes are incredibly high. A single mistranslated physical constraint can literally mean the difference between a smooth-running factory floor and a catastrophic failure. So we're going to completely demystify that process today, breaking down the exact step-by-step mechanics of moving from a physical switch all the way down to microprocessor syntax.
Our agenda follows a precise scaffold to get us there. We'll start with the three PLC languages, then look at the NO and NC duality. From there, we'll cover assembling multi-input systems, series and parallel architectures, how geometry dictates code syntax, and finally, we'll wrap up with the translation master key. By the end of this progression, you're going to have a complete operational understanding of how to map physical hardware directly into code.
Okay, Section 1, the three PLC languages. Let's establish the basics of the foundational document we're translating from today.
Dr. Nima Mahadian's approved technical document sets out our exact mission here, mapping physical logic to ladder diagrams and STL syntax. What we're really looking at is how physical inputs map directly to text-based commands. And to do this correctly, we need to realize something crucial. This isn't just about writing lines of code, it's about perfectly preserving the physical intent of the machine designer across entirely different mediums.
As we dive in, you'll see we're dealing with three distinct languages, but they all produce one logical outcome. On the left, we've got the logical intent. Think of this as the physical reality, the actual buttons, safety gates, and sensors. Then, in the middle, we translate that physical reality into visual geometry, which is our ladder logic. This maps the actual paths of energy flowing from the power rail over to the output. And finally, on the far right, we have the execution syntax, or STL. These are the literal step-by-step instructions processed by the PLC's microprocessor. So our overarching goal is to move flawlessly from that physical button on the left straight through to the microprocessor code on the right. We want to make absolutely sure nothing is lost in translation.
Moving on to Section 2, the NO and NC duality. Now that we've got a handle on our three languages, we need to look at the absolute basic building blocks of our translation.
So you might be wondering, how does the physical state of a single switch actually change our programming code? Well, it all comes down to understanding the default resting state of the hardware we're trying to control. Look, if we don't know what a switch is doing when nobody is touching it, we can't possibly write accurate code for it. And obviously, guessing wrong in a manufacturing plant, yeah, that is simply not an option. Just imagine, a mistaken switch state could mean a safety door tells the machine it's securely closed when it's actually sitting wide open. Definitely not a scenario you want.
Let's consider a normally open or NO switch. Think about the visual gap in a ladder logic line for this kind of input. Because this switch is open by default, it requires a physical action to close that gap and pass energy over to the output. Because of that, it translates into a standard load instruction in STL code. You're quite literally loading the active state of that input. But then, conversely, we have a normally closed or NC switch. This guy passes energy straight through by default. Hitting this type of switch actually breaks the flow of energy. Because its normal resting state is already active, it translates to the inverse instruction, load not. Grasping this fundamental duality is absolutely crucial. It's the bedrock for everything else we're going to do today.
All right, Section 3, assembling multi-input systems. Because let's face it, real-world machines rarely rely on just one single button, right? We need to see how these individual switches interact when they're stitched together in a larger mechanism.
So when we have multiple inputs all targeting an output, how do we actually get energy from the left power rail all the way over to the right? Well, in a typical multi-input setup, we might have two paths. A primary path might require inputs 1, 2, 3, and 4 to all be active simultaneously. That continuous, unbroken line, that is a logical AND condition. Every single one of those constraints literally has to be met to proceed. But what if we add a bypass below it? Say input 5 acts as an alternate path bypass. If input 5 is active, the energy just sneaks right around that primary path, which creates a logical OR condition. In that scenario, it honestly doesn't matter what those first 4 switches are doing, that fifth input can complete the circuit all on its own. It's a real game changer for flexibility.
That brings us to Section 4, series and parallel architectures. As these systems get more and more complex, the actual way the wires are physically run in the factory determines the structural shape of our logic.
Take a look at a series first network. Here, the primary inputs are physically wired sequentially. Energy literally has to pass through one to get to the next, which means they must be mathematically joined with AND commands right off the bat. So we load the first input, then we AND the second, third, and fourth. You can see exactly how the syntax builds logically, step by step, enforcing that strict chain of requirements. And it's only after that primary sequence is entirely locked in that we even address the bypass, appending that parallel bypass input at the very end with an OR command. Now we have to be incredibly careful here to distinguish between ANDing a group, which we do when inputs rely on each other in a sequence, versus ORing a group, which is what we do when multiple independent paths exist. Getting this wrong? Well, that means the machine behaves in entirely unexpected and, potentially dangerous ways. So, this distinction between ANDing a sequence versus ORing independent paths, it is truly the bedrock of safe, predictable automation.
Conversely, let's think about a parallel first network. Here, multiple inputs are stacked. Any single one of them provides a completely valid path, which dictates OR commands. So we load the first, or the second, or the third. But follow the path of the energy over to the right. Energy from any of those parallel switches ends up hitting a structural bottleneck. It absolutely must pass through a final gateway input at the end to actually reach the output. Because that final input acts as this mandatory gateway, it turns into an AND condition at the very end of the sequence. It's an absolute requirement bridging the entire parallel group to the final output.
Okay, Section 5, Geometry dictates code syntax. If you just compare those two architectures we went over, a pretty profound rule emerges. The hardware diagram itself is telling us exactly how to structure our code. It's amazing when you see it laid out. The spatial arrangement of the physical wire literally becomes the sequence of the STL code. A long horizontal line of switches, that just means a long list of ANDs, followed by an OR for the bypass underneath. On the flip side, a tall vertical stack of switches just means a list of ORs, followed by an AND for the mandatory switch at the end. You never have to guess the order of operations here. You simply read the ladder diagram from left to right, and you write the code from top to bottom. It's a perfect one-to-one geometric translation where the physical wiring diagram basically hands you the execution syntax on a silver platter.
Finally, we arrive at Section 6, the translation master key. We've gone over the individual letters and words, and now it's time to give you the dictionary. We're ready to synthesize all of these rules into one incredibly powerful tool.
To actually put this tool to work, you just need to follow 3 simple, repeatable steps. Number 1, identify your physical hardware layout. Ask yourself, is it wired in series or is it in parallel? Number 2, map out your visual ladder path from left to right so you fully understand the flow of energy. And number 3, write out the resulting STL syntax based directly on those geometric shapes you just mapped. Honestly, if you stick strictly to this discipline, you can translate literally any system out there.
And here it is, the ultimate cheat sheet, the translation master key matrix. This cleanly combines our structural rules on the top row with our state rules on the bottom row. Let's walk through this together carefully, step by step, just to make sure we're getting everything. First, you look at the overall structure. If your switches are arranged in a physical series, you use a logical AND. Pretty simple, right? If they're in physical parallel, you use a logical OR. Okay, second step, you check the individual switch state. If a switch is normally open, you use your standard instructions, load, AND, or OR. But if it's normally closed, you simply add the word not. So that becomes load not, AND not, or OR not. By combining these structural constraints with the resting state rules, absolutely any logic requirement, no matter how massive or complex the machine might be, can be perfectly and most importantly, safely translated into executable microprocessor code.
So we've successfully moved from the raw physical intent of a simple button all the way down to the exact syntax that drives heavy industrial PLCs. As you head back to the workshop or out onto the engineering floor today, take a look at the physical machines around you. Really look at the safety gates, the startup sequences, the emergency stops. Armed with this master key, you can now visualize the exact lines of syntax those physical components actually represent. So my final question to you is this: what complex physical system are you going to translate into code next?